Question is, using the bilinear transform, design a high pass filter monotonic in pass band 3 dB with cutoff frequency of 1000 Hz and tone 10 dB at 350 Hz. The sampling frequency is 5000 Hz. So before solving the answer, you must read 2 to 3 times in the questions repeatedly, right? So here, design a high pass filter, high pass Butterworth filter only. How to identify it's a Butterworth? Because monotonic in pass band 3 dB, right? And using the bilinear transform. So why we used bilinear transform? To convert analog filter to digital filter. So the overall question is, design a digital high pass Butterworth filter, right? Okay, let's do that problem. Given data, that pass band frequency is FP 1000 Hz and down frequency is 350 Hz. So down is nothing but stop band frequency. This Fs is stop and not sampling. So stop band frequency is 350 Hz and alpha P pass band ripple is 3 dB and stop band ripple is 10 dB. So this is pass band ripple and this is stop band, down is stop band ripple. And sampling frequency is 5000 Hz. So the sampling frequency, by use to the sampling frequency, we can get the sampling rate T equal to 1 by Fs. So 1 by 5000 is nothing but 2 into 10 to the power minus 4. In our formula, the specification in terms of alpha, right? Sorry, sigma. In formula is sigma. So first to convert Fp sampling frequency and pass band frequency and stop band frequency in terms of the sigma. So first omega p equal to 2 pi Fp. So 2 pi Fp is 1000, so 20,000 pi. Omega s is equal to 2 pi Fs. 2 pi into 350 is 7000 pi radians per second. The Hertz is converted to radians per second, omega p. So the omega is the representation of digital filter, but our formula we use the analog filter representation is sigma, right? So to convert this omega to sigma, we have a two formula. One is what? Sigma equal to omega by t. Another one is sigma equal to 2 pi t turn omega by 2, right? This formula is suitable for impulse invariance method. This formula is suitable for the bilinear method because this formula is used for a high frequency. It's a high pass filter, so we can choose this formula, right? So sigma is equal to 2 by t turn omega t by 2. Here why I used to multiply this t means, if the t value sampling rate is too small, which means less than 1 second, then you have to multiply this t with this omega. If t equal to 1 second means you normally used this formula is enough. Sigma equal to 2 by t turn omega by 2 is okay. If t value is too small, which means less than 1 second, then the t is multiplied in this omega also. So by using this formula, sigma p equal to 2 by t turn omega t by 2. So finally we will get 7265. Sigma s is 2235. So this is the pass band frequency, stop band frequency for high pass filter, right? This is the high pass filter diagram. So this frequency is stop band frequency, this is pass band frequency. So sigma s is 2235, sigma p is 7265. But first to design a low pass filter, then only it going to be convert or transform in a high pass filter. So we can't use sigma s this value and sigma p value for a low pass filter. So first to convert the low pass filter. So the lowest frequency is considered as pass band frequency. So the lowest frequency is 2235. So for low pass specifications, sigma p is 2235 and sigma s is a highest frequency. So highest frequency is 7265. So sigma s is a 7265. Okay, so this is the specification for low pass filter. Then as usual, next step is by using a formula, find the order of filter. Then according to the order, you can write the polynomial of the Butterworth filter. Then find cutoff frequency. So sigma c is equal to sigma p for high pass filter, but the sigma p, you are not taken this value, sigma p 2235. You are not supposed to take this sigma p is 2235 here because it's a high pass filter sigma p. So high pass filter sigma p is 7265. So sigma p equal to 7265. Then the transfer function of high pass filter HA of S equal to H of S substitute S is equal to sigma C by S. So this is our H of S. So in this H of S, you substitute S equal to sigma C by S. So 1 by sigma C by S plus 1, take LCM. So S by S plus 7265. So this is the analog high pass Butterworth filter. But our question is digital filter using bilinear method. So as we know the bilinear method, you simply substitute S is equal to 2 by T 1 minus Z inverse divided by 1 plus Z inverse, right? So using bilinear transformations, H of S is converted to H of Z. So for this, substitute H of S at S is equal to 2 by T 1 minus Z inverse divided by 1 plus Z inverse. So this is our H of S. So in this H of Z, substitute S is equal to this term. So 2 by T 1 minus Z inverse divided by 1 plus Z inverse divided by S. So 2 by T 1 minus Z inverse divided by 1 plus Z inverse plus 7265. Okay, then simplification, these two to cancel. So 10 power minus 4 is nothing but 1000, right? Into 1 minus Z inverse divided by 1 plus Z inverse divided by 7265. Then take LCM. Finally, we'll get the answer is this one. After simplification, using the LCM method, you get this answer, right? Here 10 to the power minus 3, not minus 4. Okay, so then only 10 power minus 3 become 1000.